Hi, everyone, and welcome back to Vector Lab. Today, we're with Robert, and we're going to discuss reinforcement fine tuning. But first, can you introduce yourself?
Of course. So yes, I'm Rob. So I'm a solutions architect at OpenAI. I actually was previously a solutions architect at Databricks too. And I just enjoy working on all things AI and all things Gen AI, as the business kind of branding term is. And I guess for myself, I cover kind of a variety of different sectors as a solutions architect. I like to cover some of the most technical coding customers and coding use cases, but I also have a background in healthcare and life sciences. So I also cover some of the AI use cases in that sector too. And I find that gives me quite a nice mixture between very digitally native, very technical use cases and some of the kind of more high level strategic thinking too.
So today we're going to talk about reinforcement fine tuning. But before we deep dive into that particular a type of fine tuning, can you remind us what are the three types of fine tuning that you can do on the platform? We know we have SFT, soft preference tuning,
Supervised fine tuning.
supervised fine tuning, preference fine tuning, and then RFT. So can you tell us what's the difference between the three? And then we can just jump on RFT in particular.
Yeah, 100%. So supervised fine tuning is maybe your more traditional fine tuning when you have an input and output pair. So essentially you have the ground truth because let's take the example of question answering, given a question, what the right answer should be. And so this is kind of quite well understood, and you can essentially get the model to learn and new things this way and to learn new behavior. A good example of supervised fine tuning as well can be with prompt compression or prompt minimization. So essentially, if you had to have an incredibly long prompt with lots of in-context examples, you can actually reduce that with supervised fine tuning, which makes you have a much lighter weight prompt. And then you also mentioned a couple of the other fine tuning. So you have preference fine tuning. Again, that's quite simple to visualize in the sense that you'd have essentially two labeled input data points or a labeled input pair. And essentially, a good example of this would be if you wanted your language model to have a certain tone or a certain style. Let's say you want it to be more conversational and more friendly and ask more questions. You can imagine showing these two different examples, and you'd essentially want to penalize the model outputting examples that were of that isn't very friendly and conversational, and you'd want to essentially reward its behavior when it does output a example that's conversational and friendly. And then the most interesting one is, I think, reinforcement fine tuning, which is actually a very different paradigm. So in this case, you don't have a labeled output example. In this case, you actually have a grader or a set of graders, which essentially score the model's output. You can go on this in more detail, but essentially it's very, very different because it's much more data efficient because you're exploring a solution space rather than just constraining the model to be, here is the right answer for this input. Because actually there can be many different types of answers for a certain input, and they can all be on a scale of how good they are and how bad they are.
So just to make sure I understood, so supervised fine tuning is your classic fine tuning. So for example, as you said, like with those examples, but then with preference fine tuning, both you can say there are different answers that could all be good, but then you want the model to provide an answer that is more leaning towards that part. I'm not sure if I expressed it well, but you said that basically you have several different ways to answer that question, and you just want, for example, to follow a particular tone, even though another answer would be technically correct. It's not the tone that you wanted.
Yeah, kind of. I think it's more like you've got two examples and you want the model to output something more like example A than example B. And it can be tone, but it could be something else as well. It's more like, I think it's more depending on the data set you have. So a good example is, let's say you were doing A/B testing for your model in production and you were able to just determine some kind of paired examples. And if you have some user signal like, oh, I like this response, tick, or thumbs up and a thumbs down for this bad one, that would kind of lead to preference fine tuning because of the input data you've collected. If that makes sense.
But you need the ground truth, whereas
you need the ground truth. That's 100%. Yeah.
Cool. And then from your experience, what are the most important fine-tuning use cases or the most popular ones? The ones that when appear, you say, okay, we may have some fine-tuning here.
It's really changing over time a lot. I think the best insight I could say is that when would you actually do fine tuning? And it's when, what problem can a model currently not solve, essentially? And not just what a problem a model can't solve, but even if you create your agentic solution and you give the model tools, you give it knowledge bases, you give it the ability to search the web, you give it an incredibly detailed prompts. Even then, if you're struggling to solve problems, that's really when you can start thinking about fine tuning. And it's changed so much because, again, you take the example of supervised fine tuning. I remember a very popular example can be classification. So let's say it was fraud detection or classifying email spam. You might have a really detailed prompt and these in-context examples describing certain phrases that you as a domain expert know lead to, for example, email spam. And then fine tuning can be better because if you've got the input output pairs, you can compress that prompt and get better results by training on that kind of data set that isn't on the web or isn't publicly accessible. However, one interesting thing that I did when I joined OpenAI is I was actually redoing some of our public documentation for supervised fine tuning. And there was one example we had where you used to do supervised fine tuning to improve models' prediction under uncertainty. And what I mean by that is basically, given a question answering data set, if there's no context that allows you to answer the question, the models just say, I don't know. It's very, very simple. 3.5 was quite poor at this, and you could fine tune, or actually even GPT-4o as well. You could fine tune GPT-4o to get a lot better performance. And the interesting thing was this was actually before GPT-5, but with GPT 4.1, it was so good at the task anyway that there was no need to do fine tuning. So that's the issue with supervised fine tuning and fine tuning, which is the models iterate at such an incredible speed that it basically can nullify some of the use cases fine tuning. And a good use case then, I think a really good example would be for fine tuning would be, what are those use cases that a generic foundation model can't cover? All of these public foundation models or large language models, particularly if you think about sensitive domains like healthcare, they have to be really hedging themselves when they make predictions. They need to be offering suggestions, but also countering them with counterfactual examples, with alternatives. And obviously that's necessary because you're addressing so many wide variety of users. That's intended behavior. But let's take the example, actually, you wanted to fine tune a model for clinical experts. In that case, you don't want a model, a tool to be uncertain, let's say, because it's going to be used as like a kind of a co-pilot. You want that model to be incredibly greedy, incredibly assertive. And so a really good use case of fine tuning I've seen is clinical trials, where you could tailor the model behavior to be just really ambitious and really confident with its prediction and just discover new things that a model that was designed to be quite cautious couldn't do. So that's my best example.
Have you seen any use case for fine tuning for tool calling? So there are so
Yes.
many. Yeah. And this is the one I've seen often lately.
Yeah, it's tool calling is challenging because you have such long change in your conversation. And when you think about this fine tuning, like a really large language model, like a GPT series model, you have to be able to call out and you have to have your server accept the requests with an acceptable latency, with an acceptable payload, whilst during the fine tuning. And so I think technically it's super challenging, but of course is very high value. And maybe the quintessential example there is coding agents. Like, it's such a huge use case. And if you can fine tune models to be really good at using those commands, it delivers so much value for developers.
So just to clarify, when you say fine tuning for tool calling, you're just teaching the model to call the right tools. Is that what you're referring to? Got it.
Yes. Was that what you said, Maria? Or was I misunderstood?
Yeah.
And then the $1 million question, or hopefully not $1 million, but often we get asked by customers, I want to fine tune because, cheaper, you can have a smaller prompt, lower latency inferences, etc. But at the same time, what I'm saying is you have to consider the one-off cost of doing fine tuning. So resources, not just compute resources, also just creating those labels when you're using, SFTFT. And so how do you know when it starts being interesting to fine tune? Because you just said you may be chasing the performance that you're going to get anyways in 2 months when they release the next amazing model. So how would you know when it starts being interesting to fine tune?
Great question. And I think there's actually two completely different answers for this, depending on the team you're working with. The standard example is if you're going to productionize a model and you're serving it at scale, you're obviously with large numbers of users and a large payload, your cost of making that fine-tuning data set and training it is much smaller than the cost of serving. So in that case, what fine tuning is really great for is you can also distill a smaller model, right? So in that case of email spam, you could go even further. You could take a really small language model, fine tune it on those high quality examples, and then you could serve lower latency, cheaper costs, and everything scales really well. So as you say, it's like, when does that cost of serving become much larger than the cost of training and creating that data set? However, at the other end of the spectrum, it's, again, back to that clinical trial use case. Like, if you think about the business value for a pharmaceutical company or a large healthcare company, that's in the billions. Like, clinical trials are so expensive and they're getting harder and harder, more administration, everything. So in that case, it's more like, actually, what if we could create a model that could really improve productivity and help the team of researchers, the team of clinicians? In that case, it's like, actually, is the cost of fine-tuning a model and creating a data set, is that really more than $1 billion? If it's not, then actually it can be worth looking into, because your trade-off there is different. Your trade-off is, what business value can I unlock with a model that no one else has access to?
And also, going back to the graders and the difference between RFT and supervised fine-tuning and preference fine-tuning, you need to only define the graders, right? But if you have a new model that's released, you can reuse those graders, which means you don't have to necessarily recreate this
Yeah.
ground truth data set. Did I
Yeah,
understand?
100%. I think that's a good point. I didn't even mention that, but I think that's even a better point than I mentioned. The really cool thing is, if you're creating graders, let's take the example of LLM as a judge, maybe. You have to do that anyway because it's best practice. And if you're going to design any agent or any system, you can't just rely on vibes when it goes into production. So if you've created those graders, it's really cool then, because if you wanted to start adapting them and using them for reinforcement fine tuning, it's much more lightweight, because it's adjusting the initial logic you've written. And then, as you say, like Lara, like, as new models come out, you don't have to go and get domain experts to label the data again. Instead, you could start adapting, adjusting, and adding new graders. So it's much more lightweight and lower lift in the long run.
Cool. So the next question is interesting because we still hear it a lot from customers, which is, when should you use fine-tuning versus RAG? Which is not a really valid question, but what is your answer to it?
So I think I would classify RAG as an example of a tool, because actually nowadays RAG or semantic search or any kind of knowledge base or a vector store, they're all kind of variations which all use similarity search for an embeddings model. So more generically, you should always, as a first, before you're considering fine tuning, absolutely optimize your system prompt and the descriptions of your tools and how your tools are arranged. For example, the number of tools, do you have any handoffs, etc., in your agent? And then once you feel like you've really eked out the maximum of what's possible, only then would I consider fine tuning, if that makes sense.
Yeah, it's also like, as you said, RAG is kind of a tool, or it's just a component of a system, right? Where the fine tuning has to do with the model, in this case, in the question we are talking about. So it's a kind of completely different things. Also, like, if you have a RAG application, you can still use a fine tune model as your kind of last point, or the entry point and last point before it goes back to the user. So yeah.
Yeah, definitely.
So do we see a demo for?
Of course. I'll share an example. See if I can share my screen.
So the whole reason we're talking about RFTs because of this cookbook that I read, and I loved it just because I love how easy it is for somebody who I didn't know anything about reinforcement fine tuning. You can just follow it end to end to run this example, right, Rob?
That's very kind words. Yes, I did it. I took a recent repass at it because obviously the API is constantly being updated. But yeah, I guess when I wrote this cookbook, it was around the time that OpenAI released a data set called Health Bench, which I thought was really interesting. There's actually, I'll scroll down a little bit because there's a nice example of like a kind of data point from Health Bench and what's it trying to measure. So essentially, Health Bench is kind of a very comprehensive benchmark which covers different conversations that people have in a medical context. So for example, there's one example here. If like you find your neighbor and they need emergency assistance, what models have different completions, and given different rubrics, how do they score? Essentially, what I mean by a rubric here is a criteria that the model must follow. So for example, if it's an emergency situation, has the model followed up that you should contact the emergency services? That's a good example of a rubric. So Essentially, that's the data set that I was very interested in. And what I wanted to do was understand actually where these models are scoring well, but it's far from like saturated this benchmark. There's a lot of performance left on the table. So where are they performing badly? And essentially, and I'll just scroll down through the code for now because it's not as interesting, but there was a rubric that I thought was really interesting, which was this response seeks additional context to reduce uncertainty, either by asking follow-up questions or suggesting what additional information would be helpful. And essentially what this rubric is trying to do is basically, when you have uncertainty, is the model asking relevant follow-up questions? And this is like a fundamental limitation of a lot of language models, which is they can often hallucinate. They often really struggle with quantifying uncertainty, and it's been around for many years. And this was one rubric where consistently models struggled with. And so I wanted to understand, if we have a bit of reinforcement fine-tuning, can we actually change the behavior of a reasoning model? I'll pause there for a moment. Does this make sense so far?
Yeah, is this back to what you were saying in the beginning, that as you were going through the documentation, you found out that older models of ChatGPT was not working well on this?
No, so that was a much more simple example. So imagine that was on a data called Squad. So that's just like, given a question, there's 3 answers. It's like A, B, or don't know. And the model was really bad at saying don't know. But it is related. This is an example of like where the current frontier of models still can't do reasoning under uncertainty.
Sounds good.
I love what you said about there's room to improve, because that goes back to the point you made around RAG. I think once I got the scenario with a customer where the model was performing badly all the time, and they were like, let's fine tune. And I was like, maybe let's work on RAG and retrieving the right context first. And then if you see there's still room to improve, that's where fine tuning can be good. But if it's performing badly on your data set all the time, probably then fine tuning is not great. So that's the sweet spot, right, that you were talking about?
Yeah, 100%. I definitely agree with that. And then, yeah, maybe just to kind of summarize this, I'll skip over the code and just skip to the interesting part, which is designing a grader. So in this case here, we have defined this evaluation prompt, which is basically, we want to score it against the rubric. So rubric is where you seek additional context to reduce uncertainty. And I gave it a couple of very general examples of where you'd ask follow-up questions, for example, for a travel use case. And the key here, this is the biggest learning I have, which is you really, although the grader or your combination of graders will output a score between 0 and 1, you want to be really careful to ensure that you have a distribution of scores. Because essentially, when the model was exploring this problem space during fine tuning, if it's just going to get a 0 output and a 1 output for some examples, it's not rich. Whereas a really rich reward would be, oh, I scored 0.2 here, I scored 0.4 here, I scored 0.6 here. So you really want that variation, and that's kind of what this prompt achieves. And then, yeah, I guess this is all abstracted away quite nicely by the OpenAI platform, but basically submitting this job with that grader on the O4 mini model. And I'll just skip down to the evaluation for a nice example maybe, which is, if I zoom in a little bit, I guess given one of these inputs from Health Bench, you'd have the output for the original model, which is kind of very certain and doesn't ask too many follow-up questions. And then if you compare that with a reasoning model, so in this case, this basic reasoning model was just O4 mini. It can have a much more detailed response, but again, it's just suggesting what are your next steps. And that's not what the behavior we want to see actually in this context. So I think I'll just skip to this tab, because I think I had it up as well. Or maybe I didn't. Oh yeah, I did. But if we skip down to the output of the fine-tuned reasoning model, what you can see is like, you've literally changed the model weights to have different behavior. In this case here, you've got a list of questions and you're asking all of the right kind of follow-up questions so that the model would need to have an appropriate response. So the key is the model's not just diving in and responding, it's collecting as much information to reduce uncertainty to give the optimal response. I'll just pause there for a moment if that makes sense.
Yeah, makes sense. And so that was an output of the fine-tuned model just with this one grader.
Just with the one grader, to keep it very simple.
Very good.
Can you have more than one grader?
Yes, and I think I would say it's very recommended to. This is like a very simple example, but in reality, you could have graders that are very simple like logic, like string matching. For example, certain phrases you'd like to see, you could have graders that are Python functions checking for certain structure of the model output. And you can also have these model graders, or essentially LLM judges, which also incentivize behavior. And I think it's really good to have a variety of them.
And to connect the dots, because you have the graders in evals, and now we have RFT. Can you reuse whatever you define in your evals with RFT? Are we talking about the same graders, or is it completely different?
Yeah, 100%. You could definitely reuse much of the logic. So just like scrolling back up to the experiment here, all you're doing here is just it's defining a prompt and then defining the grader model. So for example, in here, we have the score model grader defined in the reinforcement method. So you might want to tweak them a little bit. Just because it's a bit of a different use case if you're doing fine tuning. Like a good example is I mentioned that score, you want to be really rich, really well distributed, but it's so simple to adapt them for this.
Got it. Going back to people who want to experiment with fine tuning, but who are beginners at this. When you start with the data, one thing I wanted to ask is, when you prepare it, what are the things you should look out for? Because I know, for example, you need to address it if you have imbalances in the data, etc. And sometimes people skip the step of preparing the data and then they don't get what they want. So do you have any tips on this?
That's actually a really good point. 100%. I've actually got, sorry, this is not shared super well. I don't know if I could just do slide share for one moment. I think it's a little bit small, but I've just got a couple of examples from the most recent fine tuning run I did. And the reason why it links back to your question, Lara, is essentially you can see on this graph here, where you've got the reward over time for training. So essentially here, as the number of steps increase, as the number of epochs increase, you can see here the training and the validation reward, which both go up quite significantly. However, this is something that's really, you have to do really carefully in the kind of data prep and the grader design. The best example is by default, because it's such a massive model you're updating, you have a very small batch size when you do RFT. And what you can imagine then is, with each iteration, when you update the model weights, are you going to have rich signal if you have a really imbalanced data set? Because all real world balanced data sets are very unbalanced, because you're going to essentially have no signal sometimes. If, for example, the model really struggles with some of the data points, with each batch size, you're going to have maybe no reward, and then you're going to have no relevant update. So some simple steps I took in this example was to increase the batch size and to also sample the data set so that it had a variety of easy examples and hard examples, because then the easy examples it can do in the beginning, and then only later, after learning how to do easy examples, it can do the hard examples. So yeah, 100%, the data preparation is critical to get the best result.
And then how many samples did you actually use, like in total? So how much is enough to get a quite good model at the end of the day?
This is just 12 examples actually, and it works quite well. But even in a production scenario, less than 100 examples is plenty. You can get really strong results because essentially you can think about it at each step. The model is producing different reasoning streams in parallel. So let's say even if you have 100 examples, but if it creates 10 different reasoning paths per example, then that would be 1,000 data points it's exploring. So it's much more data efficient than any other kind of fine tuning.
And so we care more about data quality in this case than quantity.
100%.
Because wait, every time when you use RFT, it's going to build like several possible answers and then reward the best ones. So
exactly.
That's why we need such a small sample. Interesting.
Yeah, literally. I'll stop sharing.
And then should the training and validation data be in a particular format?
The format is fairly simple. It's just the input you'd have to the model regularly. So for example, the different items in the model input, the conversation. If you were doing tools, I guess, Maria, in your example, of course, you'd have to define the tools as well. But in my example, it's literally just the model input. I think the more effort is possibly preparing the graders, Lara, in this case, because you'll probably want to spend a bit of time iterating on those.
Can you share your screen again? Because I wanted to ask about the graph a bit more, just to make sure that people understand how to interpret those results. Because you said this is a fine-tuning job that you already completed.
Yes. So this is the exact example from the cookbook. I'll just make it
So people can run the notebook, clone the repo that is in the cookbook and then get this. For example, what's the difference between the green line and the purple line? I don't know if it's
Sorry, that was my fault. It's very small. The green line is the mean reward during training, and the purple line is the validation reward. So the validation data, the data is not being trained on at all. It's just being evaluated on every epoch. Whereas at each training step, so in this case, step 2, it's 1, 2, 3, 4, then you have your you calculate your train reward so that you can then update the model weights. So essentially the key is that these have a similar trajectory, because of course, if we didn't have train reward being linked to validation reward, then something's gone terribly wrong. So what it's essentially showing is that over time, these both trend towards 1, which would be a perfect score according to the grader.
So sorry, again, basic question, but when we prepare the data, so if it's imbalanced, you're going to rebalance it, make sure that it's diverse, etc. But then when you go to production, what do you do? Because in production, it's not going to be a nice, diverse data set. So how do you suggest that people evaluate, how it's performing in production?
Yeah, 100%. I think it's kind of a different question, because you'd essentially want to have all your model inputs, model outputs, and traces all logged. So for example, with an inference table, so you could see that. I think my point was more basically, let's say, take the example of having your training data set. You'd want to have a diverse number of samples, for example, in terms of how hard they are. Because if you had, let's say, naturally the data set is really bad at this rubric, and 99% of all of our data points are hard, the model actually might really struggle to learn anything, because it's so hard to find reward that it can actually use usefully to update itself. Because all of those reasoning trajectories it produces all lead to just bad performance. So it would just get stuck at a very, very low score. What I'm saying is, if you also maybe upweight the easy examples, it's able to do this initial learning, and then later it can do all of the hard examples. It can learn them because it has that base capability.
Yeah, my question was for the validation set.
Yeah.
You need to also treat that so that it's diverse, or do you want to keep it natural?
Oh, I see what you mean. I think it's fine to have it natural, because essentially it would, in that case, it's kind of why maybe the validation, I guess in this case it has a little bit of a dip over here before it rises, but there's too few examples here. But maybe in the example I was saying, you might have validation staying low for a very long time and it jumps up more towards the end, and that would also be okay because it reflects the production scenario.
Got it. Makes sense.
So when you're talking about easy examples and difficult examples, can you explain a little bit how we define?
So it's literally when you have, if I was to go back to that grader, you have a score between 0 and 1 on how well does the model perform the task. And a hard example would be out of the box. Before you do any fine tuning, the model scores essentially 0 all the time, because it's a really hard task to grade for it. Whereas an easy example might get a score of 0.2, of 0.3, of 0.1, but just any signal, because then at least the model knows, oh, if I do this in my reasoning, I at least have a small reward and I can use that to update myself. Yeah.
Cool. And then
does that make sense?
And this is then a distillation process that you have done here. Yeah? No.
Not at all. No distillation.
Okay.
It's just purely updating, the weight to the model using the grader.
Because it says distillation test.
Yeah. That's the name of my org, literally.
Yeah, this is
That's confusing.
That's good. And then in this case, it was a full update of parameters job.
Full update.
But you don't need labeled data, which is something I love, because to be honest, when you talk to customers, I feel this is the number one problem with fine tuning, because you need to get SMEs and you need them to build something. So here it's more define once, reuse several times, fine tune every time. Love it. And what about the one that's below, the chart below, reasoning tokens mean? Oh, so it's if it needs to use reasoning tokens, which
exactly, yeah,
depends on how difficult the question is.
Yeah, I think that's a good way of thinking about it. I think I was quite happy to see that this stayed fairly constant. So I think a good example of where this can explode is, and this is where reward hacking becomes a real thing. In my rubric, I also add a little clause to say keep it concise, because you can imagine if you don't say keep it concise, then the model can just go on for as long as needed to maximize its reward. So we could ask everything, all questions, just try everything in its output to try and hit that top reward. And so I try to deliberately keep this roughly constant so that it stays reasonable latency whilst good performance.
Are there any best practices on how to think about building the graders? And yeah.
Yeah, I mean, actually, if you have any more detail, maybe there's quite maybe a big, I think it's a big topic.
Oh, so for example, in the grader you showed before,
Mhm.
right? So if we go back to that, how should people think about building the graders in the sense that they have to tell the model how to rank an answer, right?
Yes. So if I was to go back to the grader, so this one is super simple.
Yeah.
So I guess the main one I think I keep going on about this, but just because I've seen such that it's so important, which is having this smooth distribution between 0 and 1. So this is why, actually, and you were saying, Lara, it can be good to have a variety of graders, because then you have much more chances of having a richer feedback, because you really don't want this to always be 0 or 1 for the signal for the model, because it's just not a rich signal. So that is by far and away the biggest tip, is like to have a variety of different graders and really encourage all the model graders to try and output a distribution of scores, not to say yes or no, because binary is just so it just makes it so much harder for the models to do reinforcement fine tuning. And to be honest, I think the second one, and I kind of mentioned this as well, which is also having some penalties, because essentially this is where the reward hacking comes in. But if you have these graders, the model is just going to maximize it any way possible. I mean, the best example of this is in coding, where if you just say to the model, make sure no unit tests fail, it will just start deleting unit tests eventually, because that will maximize its reward. And so having graders say no unit tests have been deleted is a really good example. So it's a bit domain specific as well, and a bit depending on context.
Amazing. And then how can you have a view on all the graded answers? Can we have a view of that at the end of the fine-tuning process?
Yeah. So you could do that within the platform as well. But in my case here, all I've done is just outputted them to the Python notebook for visualization, because I think I only do free test examples just to keep it kind of nice and concise. But 100%, what would be much better is to have your nice inference table and to have everything logged with the different scores, so you can come back to it over time.
Also, I want to see this distribution of the grading.
The scores.
Yeah, the scores.
Yeah. So in this notebook, I did a little example above, and maybe just to scroll up to the code for a moment. But essentially, if we just take GPT-5 with a simple prompt to say, given that rubric from Health Bench, given my data that I filtered, is our data diverse? And what I mean by that is, I don't want to see half the examples saying 0 and half the examples saying 10, because that means it's like some are really easy, some are really hard. There's nothing in the middle. And what I was kind of quite careful here in this example was to make sure we at least had a decent distribution, so that when it comes to the fine tuning, some examples are moderate complexity as well, so that we are able to kind of make that jump easier. Does that kind of help a little bit?
Yeah. Yes. That is on the training data set, let's say, training validation data set. What about the ones in the fine tuning process?
Oh, like during it, if I go back to the job, for example, let's just go back to where did I put the job? Oh, it's here. I might not have screenshotted it for this example, but yeah, essentially this graph only captures it high level. So for each example in that batch, on average, they scored 0.1, 0.2, 0.3, 0.4, etc. So there's not a fine-grained view in this example.
And can you explain for people who want to start what a checkpoint is?
Yes. So a checkpoint is essentially, if I just zoom in actually, during this run, we're going to have in total, we have 18 steps. And in the checkpoint, we have checkpoint 12, checkpoint 15, and earlier checkpoints. And these are essentially snapshots of the model weights. So there's a couple of reasons for this. One might be actually, maybe I end up overfitting to the validation data set. If I do some runs on my test data set, I actually would want to go back to an earlier checkpoint to make sure it generalizes better. But another good example for this can be, take Maria's example earlier where we have, let's say we wanted to fine tune in the future, we wanted to have lots of tools and our job fails because our tool failed because it was depending on an external server. We'd want to be able to have that checkpoint so we could restart the job and not have to restart it right from the beginning. Yeah.
It's a copy of the model and the state of the model at that point in time, really.
Yeah.
But then you can use it and expand it or use it to serve it.
And so any tips on how to choose the right checkpoint for your task? And as you say, find this balance between having something that's general enough, but at the same time, like where you can see good performance on your validation set.
Yeah, definitely.
Yeah. Any tips on how to choose the checkpoint?
I think if you were choosing it based on during the job, it would be if you start to see this validation reward going down. So let's say at this point here at checkpoint 12, we start to see it decreasing. We know that it's not going to generalize well to our data. So we'd want to start thinking about using earlier checkpoints.
Because then it starts overfitting to the training data. Got it. Awesome.
Amazing. Thank you, Robert.
Thank you.
Thank you so much.